The presentation I'm giving for Antonio Iovane, who couldn't make it in person, so I'm going to present on his behalf. And Antonio, I'm just going to introduce him real quickly. He's about 65 years old. He studied electronics when he was young in Naples University there. Yeah, there's some people there. I'll just wait for them. I'll just wait.
We have a few more people here.
So, let's talk a little about torsen. So what is a torsen? It's a very delicate and sensitive balance. It consists of a thin aluminum disc, about 12 centimeters in diameter, weighing 0.1 grams, suspended in the center by a single filament of natural silk. And I think what the editors are doing with the importance of this torsion balance with the silk is that there's very little, when you twist something, it winds up, there's this potential energy which tends to want to bring it back. And this type of balance, it has very little of that. It doesn't tend to wind up and want to return. It's more of an indicator rather than a measurement. And there's references for all this. I didn't study this for 15 years like Antonio did, so I hope to be faithful to his intended message. It's sealed in a non-vacuum container, so that's he specified that in his paper. There's air in there. It's electrostatically sealed, but not magnetically shielded. That's an important point there. With an automatic monitoring system of the azimuth of a reference on the disk, so you could know whether it rotated. The Torsen data. So a little bit about the data collected by Torsen. So Pugach's data spans a long period of time. It goes from, I think it goes from one solar maxima or minimum, the whole solar cycle. It covers different phases of the current solar cycle, from minima to maxima. And it shares a common characteristic with many other devices of the same family. Of the same family, meaning the devices that have a freedom of movement around a pivot point, such as pendulums, spring mass gravimeters, and torsion balances, whereby positive results are shifted in time relative to the optical eclipse. So a lot of times the optical eclipse will appear at a certain point in time, but this anomaly is registered maybe 1 or 2 hours later. Up to hours is the order of magnitude.
Could you just expand on what the second point is?
It covers different phases of the current solar cycle from minimum to maximum.
Okay, what do you mean?
Well, what it means is that they've been collecting data with these devices for a long period of time.
But not saying correlations.
Oh yeah, there's seeing correlations, but we'll get to that.
Okay, good.
I think about 7 years. I think it's something about 2 or 5 roughly.
2 or 5.
2 or 5 roughly. As I if I correct.
There's graphs, there's data, so you can see for yourself and make your own conclusions. And if you have questions, his email I can.
I know Antonio.
You know Antonio. Correlations. You're asking about correlations. Okay, so the Torsen activity, correlates grossly on the long term with sunspot activity. And it also correlates with NOAA data on geomagnetic activity and geomagnetic anomalies, and there's correlations. Okay, so it correlates, the activity correlates with the sunspot activity grossly. It correlates with data from NOAA on geomagnetic activity. Antonio found that through his research that he found correlations between geomagnetic activity and solar eclipses and eclipses. And so then the question comes, and this is where his intuition, this is where Antonio's intuition kicked in and said, could this Allais effect just be an artifact of geomagnetic disturbances caused by the lunar wake? Right? And so that's what we're going to get into a little bit more deeply. So here, I don't know how well you can see this, but if you don't see it, I'll explain it to you. So on the top, what we have is Torsen activity between the 1st and the 17th of January this year, 2014. So we see in blue is the right. So this is the activity registered by the Torsen. So what is plotted in both cases is standard deviation computed over a moving window of 60 data points, 1 hour, the blue and the green. So these are variations, what we're seeing, variations. And these computer standard deviations have then been smoothed over 1,000 points moving average, moving window, sorry, the red lines. So these are standard, these are variations, and these are times when there's not much activity. Not much variation, right? And this is all data collected from both batch and over here. So this is the Torsen activity, and down here in green, this is the magnetometer data from GOES 13 satellite. So we see some, when it's quiet, it's kind of quiet. When there's a lot of, so you can interpret it how. So that's just a little comment about the correlation. But we're going to see a lot more graphs with correlations. So the lunar wake, what is the lunar wake? So by lunar wake, we mean the eclipsed solar wind. So you have the sun, the solar wind, and you have the moon here, let's say, and then so on the shadow of the moon, right? There's not as much solar wind as is in front of it, right? So that's this wake that we're talking about, right? And it's not coaxial with the optical shadow of the moon. It's angled, right, to the Earth, and follows more or less this Parker spiral, right? Like we see on comets and so on. And the wake is also turbulent. It's not a very static. It's not like a shadow, like my hand here. It's still being researched and studied and so on. So, but that's the whole point here, is that it's not exactly, doesn't coincide exactly with the optical lunar eclipse. And so therefore, it could explain the time offset between geomagnetic anomalies and optical, the optical eclipse. And satellite data reveals that geomagnetic disturbances during eclipses, and this is what, through this intuition, Antonio went and researched and found that there was correlation between eclipses and geomagnetic disturbances. All right, so here's one. There's 7. So this is a solar eclipse in Shanghai on July 22nd, 2009. So what we see here is that there's a very irregular, what are the units here? We're saying, it's in nanoteslas. So we have nanoteslas here, so we have the intensity. And if there's 2 different satellites, there are different longitudes, right? And these represent day and night, right? So, and there are different longitudes, which explains why they're a little bit out of phase, right? Because they're not measuring, they're not at the same point, right, around the Earth. And then all of a sudden there's the eclipse here. It's quite striking, that it's you have this smooth sinusoidal, and then all of a sudden you have, whoops, something happened, right? So pretty interesting variation there. So Leo Linucciella had observed abnormal behavior of a ball-borne swinging pendulum on July 22nd. The GOES 11 and GOES 12 satellite magnetometers say that the geomagnetic field was disturbed in the morning of July 22nd. Some persisting noise in the days after.
Something happened 2 days before, didn't it?
Something happened 2 days before as well. Yeah. That's more than a couple of hours. On July, because the sun was spotless, on July, okay, so you'll notice, I noticed that in his paper he talks about when it's a quiet sun and when it's a noisy sun, to not mix, to not confuse the disturbance caused by the eclipse with that caused by solar storms and so on, which cause disturbances. Here's it on July, August 2009, the sun was spotless. Sunspot number equals 0 since July 12th and up. July 12th is, that's 30th. Up to August 30th. The July 22nd solar eclipse occurred in a period of very quiet sun. Nevertheless, the satellite magnetometer data for the period of the 17th to 25th say that in the morning of July 22nd, the solar eclipse day, there was a remarkable magnetic disturbance. I interpret this disturbance as an effect of the lunar wake on the magnetosphere.
Excuse me, one question. The eclipse is after the eclipse, how many hours? 24 hours or more?
Let's see. Here he says, observe, I don't know here.
I mean, the one you can see where you had it. Just to your wife. That's
so
minimum.
Duration of the eclipse.
Hold on. Here.
There are some minimum afterwards.
Sorry?
The minima after the eclipse are after.
Oh, the
Like
minimum.
those.
Oh,
Those
these.
are, how many hours are those?
This
Like,
is 24 hours. This is the night and day.
So
cycle.
24 hours or 8 hours or 16 hours?
July 22nd. So this is July 22nd, July 23rd. So from here to here is 24 hours.
Okay.
From here to here is 24 hours.
Okay, no, it's easy because in some of the
So from peak to peak is
Yeah.
it's 24
in some
hours.
of the observations by the Turku group in some eclipses, there have been some events before 24 hours and after about 24 hours. So it is not a matter of just being next to the
Yes.
optical eclipse, but there are some effects that come about 1 day or 2 days before and after, and they have also been documented by the Turku group in Malacca.
Yes. So Antonio's explanation for that is well, for one, the measurements of the magnet, the satellites, they may be in different positions, and the Earth rotates, but it doesn't rotate its magnetic field with it, or the magnetosphere stays. The Earth doesn't. The magnetosphere doesn't. It's with respect to the sun, the direction of the sun. So the satellite might be at a different position, and by the time it gets around to measuring it, or maybe measure it before. So I can read. He put that to me as well.
I can ask you.
Okay, next one. Solar eclipse over Australia and the Pacific Ocean in the night of November 13th and 14th, 2012. Olinichi al observed anomalies both with torsins and pendulums. The satellite graph in figure 3 shows that the geomagnetic field was disturbed in that night and early morning. So the night and early morning, November 13th, 14th. So geomagnetism in the night between November 13th and 14th. These are still the GOES. This is the GOES 13 and GOES 14 satellites with different longitudes. Just for you to know the difference, one is at 75 west and the other one is at 89 west. In other graphics, they were 75 and 136, so there's more of a difference in the phase there. The signal that we're observing here. So the solar eclipse of November 3rd over Atlantic Ocean in Africa, Pugatch detected abnormal behavior of 3 torsins. The satellite data shows a disturbed geomagnetic field in the morning of November 3rd. So this is the one that he refers to as
the question. On both the previous graph and this graph, it shows before the drop-off, you have a peak that's higher than previous peaks. But I don't see on there where the eclipse starts, so we can't see how it relates to the eclipse. See, if when we look at the graph, yes, I understand the 24 hours and all that kind of stuff, but where is the eclipse exactly
Exactly.
happening?
It does say 13 to 14, so it looks like it's going to be close to that.
So is that, so the point is, I don't know, that higher peak, which is, in the previous graph and this, which are both higher than the other ones,
Yeah.
right? Does that come prior to where the start of the eclipse, or is that at the beginning of the eclipse? Because there seems to be two effects. An effect this way, which is lesser, but it's still up that way, and then an effect to the minimum. So both effects take place. But it doesn't show exactly on there where the eclipse starts.
That's a good point. It would be more. It would be useful to have, let's say, a line or
Shading.
Shading.
Yeah, where it becomes more intense at the full eclipse, where it's, you have lesser shading at the beginning of the eclipse and after.
Like shadow there, but it's actually pushing
You
it
have
out
a
to the
shadow,
side.
so you can see what's happening.
Yeah.
Yeah.
I'll just take a note of that for Antonio.
Get the fraction.
And by the way, these are all in UTC. So the times are in UTC. So sometimes the time zones might be different. It's not the same time in New Zealand. Okay. So let's look at another one. So number 3, solar eclipse of November 3rd, 2013. That's just about a year ago. Over the Atlantic Ocean, Africa, Pugash detected abnormal behavior of 3 Torsens. Is that the same one as before? No, that's 2012. Okay. Detected abnormal behavior of 3 Torsens. The satellite data show a disturbed geomagnetic field in the morning of November 3rd. So, Torsen observation. You know what? I think this is.
No.
This is not this. This is the next one. So, that's my mistake. Sorry, I prepared these slides. Okay. Satellite data show disturbance. No problem. So here we have a start and an end. Torsen observation of the solar eclipse. The solar eclipse starts and ends over here. So we see what we're looking at here is the Torsen response in degrees and the time, right? So the Torsen is starting to get a little crazy over here just before the eclipse starts and then drops off back to a steady state later on. And these Torsens earlier, it could be, I don't know if they're positioned in the same part of the world, these Torsens, that might be something to, I presume that the Torsens are not all in the same location, or else it wouldn't be much fun. Okay. And again, Antonio's comments, I interpret the geomagnetic disturbance as a trace of the lunar wake. So, important thing to note that I didn't mention before is that one of the things that got Antonio to thinking about the lunar wake and so on was that during the solar eclipse, he found that the Torsen device had activity. But then something strange happened was in between eclipses, there was no eclipse going on, and it was registering anomalies. And this was during the solar maxima, when there was a lot of solar storms. So that's where he started correlating things. And apparently, I think the Torsen, my question would be, well, do we see the Foucault pendulums changing direction when there's a solar geomagnetic disturbance? So I don't know. I'd have to get more details on that. But the Torsens,
They're aluminum disc?
it's an aluminum disc.
So it's not a magnetic, right? Maybe a length of day change?
Because aluminum is not a.
Well, I'm just thinking.
I know it has specific electrical properties. Aluminum. So yes, Bill.
There's an explanation for its torsion. It's only electrostatically shielded, and so the charged particles coming from the sun or in the magnetosphere that are moving with velocity are not going to be shielded. And so they will register an effect on his torso. But he's not expecting that electrical effect. He's expecting it to be due to magnetic fields. But it will be due to Lenz's law. He will get an effect.
You're saying that even though it's electrostatically shielded, it may not be due to induced eddy currents, but it may be due to charges going traversing the shield?
Yeah, charged fields produced by velocity of charged particles. The particles don't have to.
Oh, right, yes,
but
I
the
remember
fields
that.
will go through.
Somebody mentioned that specific type of field generated by moving particles is not immune to Faraday cages or something.
But see, when you have an eclipse, the magnetic field of the Earth, which has a lot of charged particles in it, is disturbed, and some of the particles move faster than normal. And when you have a solar flare, you get the same thing from the sun. The particles coming out are moving faster than normal, and so that's going to produce fields that will get into his torso.
Electric fields, not necessarily magnetic fields, but the electric fields could go through the electrostatically shield. Okay, I got you.
Yeah, and in both cases, there's similar kinds of activities charged particles.
Yes.
So that might possibly explain some of the things he's seeing.
Okay, that's a good point.
And that the magnetic field is pretty large, so even before the moon gets directly overhead to block the sun, you're going to get an effect.
Okay.
And so we were looking at the peaks before the eclipse occurs that were in the readings, and that would be also explainable in this regard.
Okay, I took a note of that. Oh, sorry, the last little part there? Also, you said also?
Well, the peaks before the eclipse occurs.
Yes.
They're peaks that we see.
Yes.
And that would also be explained by the same effect because the magnetosphere of the Earth is large. And so as the moon moves to be close overhead, it's going to be disturbing that magnetosphere for quite a distance.
Right.
And so it will produce effects before it's overhead. So you're just looking at the time when you're blocked.
Yes.
You'll see that. And my wife and I, we went to a physical eclipse of the sun in Newport News, Virginia, which was in the 1960s. And we noticed that the light fluctuates wildly during the time of the eclipse, and all of nature gets quiet because of these fluctuations.
Were you talking about light, natural light, or light and
Natural light, but that's just due to diffraction. But all these other things are going to be diffracted also and altered in there, and so there's going to be a lot of fluctuation.
If that was the case, then even when you don't get an eclipse at the new moon, you should get some effect as well, shouldn't you?
Yes, and in nature you see it. The hunters will tell you the best time to go hunting is the time when the moon is overhead. And why is that? Because the animals are more active then than on any other day or any other time. So if you want to be able to see them, that's the time to go.
All right. Okay. And what's down here? Okay, so here's the Torsen, and down here is the satellite data for the geomagnetic activity. So there's a correlation, assuming that they're lined up properly. There's lines here, so I'm assuming they're lined up properly. And there's a correlation. So, number 4, solar eclipse of January 26, 2009. It's an older one. Fugaccia and Allais observed correlated abnormal behavior of Torsen and paraconical pendulum. That's the Foucault pendulum, isn't it? The paraconical? So figure 5 here is the satellite magnetometric trace showing steep variations in the morning of January 26. I interpret them as being caused by the lunar wave. So here we have the magnetic, but we don't have the exact time. And so I'll make a point of that. Maybe it's better to have them all lined up so you can see exactly the timing of the the instruments, the satellite data, and the optical eclipse. So where's his? I believe it was
The previous day. Morning of
January 26th. Is that one? A little mess, a bit slightly messy. And then there was this kind of funny one. I think he mentioned that in his in the full paper. There's a mention also of this, but I don't remember why. You can look at that after if you guys want. It's getting a little late. We've got supper soon. Okay, lunar eclipse of October 8th. Moon at opposition. So this one is a case of when the moon is, you know, if you were on the moon, you would see an Earth eclipse. You know, so we call it a lunar eclipse. So the sun is here, the Earth is here, and the moon is over there, rather than the moon being between the sun and Earth. And I'm not sure why exactly he put that in there, but I think the reason was that he mentioned it was the instabilities in the geomagnetic field, which were caused by normal or this interesting new. Okay. Recently, Falaki installed the new Torsen at a different location. He recorded the trace of figure 6. Which shows Torsen activity in the mornings of October 7, 8, and 9. This interesting new test made at a new location of the device confirms that the Torsen responds to instability of the geomagnetic field. So in this case, it wasn't responding to the lunar wake, it was responding to geomagnetic, and I guess that might be, I don't know why he put that in there, but I suppose it might be in case somebody says, I'm speculating here. I was going to ask him the question, but we didn't have time. In case somebody says, well, we registered anomalies when the moon is on the other side. Not sure. He says here that the bottom figure shows the satellite data for the same period. In this case, the Torsen detected ordinary geomagnetic disturbances, stronger in a non-eclipse day and not the lunar wake, which was on the other side. The eclipse was a coincidence. Put that in there. I'm not sure why. Okay, solar eclipse, May 31st, 2013. This is a pretty dramatic one. Early morning, Iovane recorded abnormal tilts of a stationary pendulum. Unluckily, he recorded only 8 hours centered on the eclipse, while the geomagnetic field was strongly disturbed since a couple of days, and the effect of the lunar wake is not clearly visible due to the general geomagnetic conditions. Right? Another correlation there. Another eclipse, August 1st, 2008, Gudev et al. Claimed to have observed correlated anomalies on their instruments, but there is no strong evidence of the lunar wake and satellite data. In this case, the satellites I'm using as reference might have not seen all the effects of the lunar wake because their longitudes were too far from the longitudes of the eclipse path. Anyway, the August 1 curve is not completely free of disturbances, and as an example, the blue curve, instead of being quasi-sinusoidal, shows a V-shaped dip. So he just added that, oh, here it is, the V-dip. That's one of the satellites registered the V-dip in all of the videos. Conclusion. So the conclusion is that the Allais effect correlation with the optical solar eclipse has been loose most of the times, and no predictions on its detections have ever been successful based on the optical eclipse geometry. I suggest, Antonio Iovane suggests that the abnormal behavior of the Allais effect test devices is due to eddy currents induced into the test masses by the geomagnetic disturbances caused by the lunar wake hitting the magnetosphere. That's the presentation. Do you have any questions?
And then what's the take-home message from this?
Well, the take-home message is that perhaps it's not some that it could be a simple mundane explanation for the Allais effect, and without new science or exotic physics and things like that. I guess that's nice.
So basically, you're saying the take-home message is we don't know.
No, he's saying he knows. He says he sees it.
If he knows, then
It's right here.
what? The cause for the lunar wake hitting something, and he's not sure.
Well,
I mean, you see,
he's got good correlations. There'd be some, I guess you could continue the research to verify.
just because, secondly, just because the two things are correlated,
Yes.
doesn't mean
Well, he's got
the conclusion is valid.
Well, of course, I agree with you. I mean, he's got a cause and effect explanation. It's not just a statistical base. He's got a cause and effect explanation. His cause and effect is that the lunar wake creates not an inconsistency, a discontinuity in the distribution of the solar wind. It's a discontinuity, and this discontinuity, because it's variations in the geomagnetic field that induce these eddy currents. So if you have a solar wind during the quiet sun when it's just shining bright and nice and clean without any mess, but then the lunar wake comes in and there's this discontinuity and you have the large variations. And he mentions in his paper that his thing is based on steep variations.
But it doesn't relate to the optical geometry.
Well, that's because, according to Antonio, the wake, or the shade, if you will, it doesn't coincide with the optical shade.
Or does it coincide?
It doesn't. You know how when you look at when you see comets on these, the tail is a little bit, like a spiral. It follows the spiral.
Because the solar wind is doing about typically 300 kilometers per second, whereas light doing 300,000.
Right.
And so it will take a matter of hours before it gets
Well,
from
not
the-
only that, but light comes from the sun in a straight line, whereas the solar wind, it doesn't come in a straight line, it comes kind of curved. So that's why it's hitting the Earth on an
It is
angle.
coming in a straight line, but not relative to rotation.
Well, somebody showed the heliospheric current sheet before. It kind of spirals out.
It's got a curve. It's all traveling out in a straight line. It's like the water sprinkler, right?
Yes.
It's throwing water out in
Right, I
straight
got you.
lines back
Okay.
to the-
Right.
the sources.
So maybe he's mistaken. But when you look at
No, I'm
comets,
right.
when you look at comet tails,
They point away from the sun.
and their current and so on, so they won't point straight away from the sun. They're on this.
Because they're showing the past. They're showing the bit that left there now it's moved across to here, so it's like that.
Oh, is that what it is?
Yeah, it's the fact that it moved.
Might be interesting if it correlated to length of day changes, because some of these effects change length of day, which is rotation on their impact. So might be curious to
That's
see
right.
if there's a relationship to length of day.
The length of day varies quite a bit. Yeah.
Oh, yeah,
It
that's
can with different geomagnetic disturbances and earthquakes, changes in length of day.
And the Earth somehow returns to its stable thing, and it stays stable.
No problem. It's all over the place. Right, from a number of causes, from solar cycles, from
But if we look at
the wind blowing against the Himalayas, the monsoon blowing against the Himalayas, actually, you can measure it in the day.
But if we looked at a purely like Newtonian way of looking at things with the gravity and all that, if you do a little disturbance and you hit the Earth, like let's say slightly goes off orbit or something like that, it should keep going, blow away. But it seems to find its stable point, and I'm getting off topic here. But
No, it's only internal to do it,
yeah.
so it's not really good.
Does that answer the question a little bit about the
Yeah, a
lunar
little
wake?
bit.
And
That's
another
the
point.
key word,
Yes.
little bit.
Another point is that I'll get to you, Bill. Another point is that the models, the lunar wake is they're mostly statistical models. They're macro. It's not very. It needs a little bit more research. It doesn't have a lot of research. There isn't that much research available on this lunar wake. But one thing that they do know that it's turbulent, because as it leaves the solar wind, it leaves a little void, and then so there's stuff going in and out, filling the void and so on. So there's some turbulation there. Some turbulence. Excuse me. Did I say turbulation?
Like tribulation. You've
There's
been reading Bible too
turbulence,
much.
so that also contributes to the factor of it doesn't coincide exactly with when the lunar eclipse is, and it would also explain why sometimes it's before. And another point is the satellite and the satellite data also maybe it has to be adjusted for the when they pick up the geomagnetic activity. Bill.
I've been in a total solar eclipse about noon, and the time when the diffraction patterns are coming and the light is fluctuating a lot is much larger than the time for the optical eclipse of the sun by the moon. The time
Before and after?
Yes, before and after when you have very noticeable variations in the light. During the total eclipse, it's dark. Well, not completely dark, but it's relatively dark. But before that, the variation in the light is quite noticeable, and it's you can almost see like stripes or lines moving across the surface of the Earth from these diffraction patterns. But that's optical light that's being affected. So these charged particles are going to produce a much bigger effect in terms of time width. But just with the optical, it's much larger than the time of total darkness.
Not just with the optical itself is already...
Yeah, because the light is diffracted from different parts
Right.
of the moon,
Right.
and so it comes at different angles, and it's a kind of circular pattern on the Earth, and you can see it when you're there. You can see these lines passing by, and the lines are lighter and darker, lighter and darker, but not totally dark. But you can see these patterns going by. And so if you were just saying what the optical effect, well, it's much wider than the total eclipse. It's because of the diffraction patterns.
Yes, I can comment on that. Yeah, but I didn't want to say. Actually, the point of the beginning of when the penumbra enters in is called C1, usually in the parlance of the astronomers. C1, and then you have C2, which is the moment when totality comes in, and then you have C3, which is the end of totality, and then you have C4, which is the end of the umbra on the outside. And so, one part is about minus. Totality usually from C3 to C2 to C3 is about minutes, 2, 3, 10, up to 10 minutes roughly. And the other part is about 1 hour from one to the other side, or more than 1 hour.
Yeah.
And so when you talk about the optical part, usually you are concerned about whether that comes before C1, what is between C1 and C2. Some of the things that was shown before by the other Italian fellow, the one Valentino, that dip there most likely was between C1 and C2. And also the one of the Chinese that was shown this year by Andrews was between C1 and C2. But sometimes those dips come before C1, and that is definitely before the optical part.
Right.
And that is something of concern.
The charged particles, I think, will come.
I understand that. I understand. And this is why I think what is involving those things is scattered. So what I not understand very well with Antonio's idea, new idea, is that some of Pugache's initial measurements were done in Kiev. And Kiev is usually far away from most of the optical paths. And so that was far away from this, and so in that scattering of whatever it is, charged particles or a region of any kind, that will be far away down to Kiev, about 2, 3, and sometimes 5,000 kilometers. Because it was very far from the path. And he obtained results there also. So, but at that time, he could use a different kind of balance. So that is something that different. So that's something to be wondering.
You're in communication with Antonio, right?
I know Antonio. I mean, I wrote the book on. I mean, I did the book on Allais.
Your reference.
And he contributed to that history book. And I also know Polish.
Yeah, I'm trying to figure out from what the presentation from a different angle of more of the Lesage screening effect, and which is directly involved with gravitation. Okay, and since light would not act in the same way as the screening effect, which actually could cause the effect, tidal effect, or whatever you want to call it, at the Earth's surface in a wider area. That I'm kind of interested in that peak before the valley. Okay, that would be an indication, if you look at this, that what you're getting is an effect which is broader than the optical effect, and which then needs to be explained. And if you're looking at the Lesage screening effect, as I said, the likelihood it would be broader because of how the interaction would take place there. And then the question is, how does it produce that peak before the valley? That's my only comment on that.
I'm not familiar with that, the screening effect, but maybe somebody else has that. Somebody
If you're
can
doing
comment.
research, then most of the mass of the sun is not that big. It's only that little tiny bit like that. So they could force out much sooner than this one said. Right?
There's contact information for Iovane at and at the end, I wanted to thank, don't want to miss that. Antonio Iovane thanks Professor Alexander for using it. I think we should wrap it up because we have supper soon.